recording is about to start. You should get a notification at the top of your screen saying that it is being recorded. And now we can get started. So on the next slide, I'll kind of go through the webinar procedures before handing it back over to Aaron to start his presentation. So for any questions or comments that you have, please do use the chat or the hand raise function with Microsoft Teams. When you're chatting with us, let us know your name and your affiliation. You can either type out your full question or your comment. Sometimes that takes a while, so you can just simply put question/comment. And once we get to the next Q&A slide that are put into the presentation throughout, we'll unmute you in order for you to bring up your question or comment that you had. If you're joining via phone, you may need to press *6 to unmute you. But we'll cross that bridge when it comes. If you feel like you're talking and we can't hear you, we'll let you know and we'll troubleshoot at that point. So this is the chat function. You'll see it kind of looks like a little speech bubble that you can press on. You'll type your message and you'll press on the little paper airplane symbol to send it to us. And we'll all see that you have a question or comment to be addressed at the next Q&A slide. And then Aaron, if you go to the next slide, it kind of gives instructions for that hand raise emoji. It looks like a little high five. So if you hand raise your hand during any point in the presentation, we'll see that next to your participant list. So you could do that instead of using the chat function, and we know that you have a question. Again, it works the same. You'll be unmuted during the next Q&A slide. And we will troubleshoot any muting issues at that point. If you have any issues with the webinar in general and it's not pertaining to the presentation, I'll be monitoring the chat the entire time. So hopefully I'll be able to respond back to you in real time for those questions. But yeah, without further ado, thank you all for being here, and I'm going to hand it back to Aaron. Thank you.
Great, thank you, Amanda. Can I do a quick sound check with you and make sure I'm coming through loud and clear?
Yes, you are loud and clear. Thank you.
All right, awesome. Well, thanks everyone for joining. We last got together in June. It's been an eventful few months, and we had a great discussion in June, both about the preliminary calibration that we presented. Got a lot of your feedback on that in this June 3rd meeting. And then we also heard from SCORP, part of the June 16th meeting, about how those flow data were going to be combined with ecological data to perform the ecological assessment as part of the project. So this is just a recap in a meeting 1 through 6 that we've had as part of this project. But this meeting really continues on the discussions we had on the back in June in both of those meetings. So from those previous meetings, and these are specific to the to discussions and resolutions we've had about the hydrologic model. We talked about the model construction, what we're representing in terms of processes and features in the watershed, how we were going to do the calibration, where we were going to do it, and what metrics we were going to do, which conditions, which watershed conditions. We'll get back into those. And then notably in June, we heard from you about sort of what you saw in the calibration, which matched a lot of what we saw in the initial calibration of areas where we could improve, some areas where we questioned the reliability of the model a little bit, and could see some better fit. And from that, we had already at that point in time an isotope study in progress. We didn't have any results from that yet, but we certainly saw some promise in that to help resolve some of that, and that's one of the things we'll talk about today. So certainly this springboards on the what we heard from you in June about model calibration, and then finally we talked back in both January and June about the areas that would be modeled with different models. There's we'll hear a little bit more about the GS flow model that the Santa Margarita Water District has developed for the San Juan Basin, and sort of what parts of the watershed that is the more reliable model to use for hydrology, and then the areas that are served by the Lspc model that we'll spend most of the time today talking about. So we are springboarding on previous resolutions, but the agenda for today is to revisit with you the revised calibration that we got after we incorporated isotope data and the input we got from you in June. And with that, we obviously updated the reference condition, and which we presented in June, but with a different current condition calibration. Obviously, the reference condition, when you remove urbanization effects from it, looks different as well. And the last piece that we previewed but did not present results of in June were the scenarios that we're now using the model to evaluate, including looking at future versus past climate and how that affects model results, as well as water conservation. And so those are the sort of objectives for today, is to present to you the updated results from each of those. And you kind of see the agenda. We're going to take a break in the middle, sort of between where we talk about model updates and when we move into describing the different scenarios that have been evaluated with the model. And we'll break basically whenever we get there, potentially a little earlier than 11 for the break. Because I think what you really care about is the scenarios and a little less about exactly how we updated the model. So we'll try to move through that first part a little more quickly, out of respect for what I think you're likely more interested in. So there are, just to signpost what we're hoping to get from you today, we are nearing the end of this special study portion of this. And SCORP is going to be doing a lot of work with the modeling results. I think what we're looking for is, are there any significant remaining concerns with the performance of the model that are really critical to resolve to support the study? And then clearly any model can continue to improve with more data, with further evaluation of elements. And so we can also create a parking lot for things that should be prioritized in the future if there's ongoing budget to revisit those. So that's the essence of what we're hoping to get from you today. We'd like to hear any comments you have today. We'll take notes and we'll develop responses to those. We also, over the next week and a half, if you have any written comments you'd like to follow up on, we will take those until the 24th. And we have, at the end of the presentation, some guidance about how to submit those. You can, of course, just email them to Amanda, but there's also an opportunity to submit them through the website. Okay, with that, brief study orientation. Many of you have been with us for previous presentations, and so we'll go through this quickly so as not to dwell on the same slides we've used before, but for those who haven't or need a little refresher, we'll go through these. So the objective of the overall study, not simply the hydrologic modeling part, but the overall study, is to develop tools and data sets to inform flow management activities by the MS4 permittees. So that one of the key goals is to ensure that what the MS4 permittees are doing with the water that runs through the MS4 system and drains through outfalls is supportive and aligns with the overall watershed rehabilitation and water resources management efforts. So with that, these data sets can also support permitting of future projects, understand how any flow modifications associated with those projects would support the watershed rehabilitation efforts, and through these tools also identify those projects that have the greatest bang for their buck effectively and can help prioritize funding for those types of projects. So those are the primary overall study objectives. And the overall approach involves what we're doing today, which we've been doing all along with stakeholder coordination, a hydrologic assessment, which is started first, but has spanned as we've gotten better data and continue to improve, and the flow ecology assessment using these hydrologic data along with the ecological data and models to develop a flow ecology model. And that's also been moving in parallel ever since the first part of this year. And you'll hear more about that in December, early December, December 2nd from the SQUIRP team. And through this, developing flow ranges that would support focal species. We talked about focal species back in June and had a follow-up call to talk about that again over the summer. So one of the key questions would be what flow ranges would be needed to support those, and using those by the permittees, using those data sets of current conditions and what flow ranges would be desirable to evaluate management actions, or what we like to call BMPs. So we're looking at, as part of this, you'll hear about current conditions, you'll hear about reference conditions, and you'll hear about future scenarios. And we'll get into those in more detail as we talk about them later. You'll also hear about different metrics, and you'll specifically really hear about these metrics in a couple weeks in the beginning of December, when SQUIRP takes the continuous time series data that we're giving them at a lot of different points in the watershed and turns them into functional flow metrics that have predictive relationships, or at least associative relationships with biological conditions in these waters. And so these metrics span the whole hydrograph, the whole annual hydrograph, from the summer base flow to the winter peak flows to everything in between. And so, if it feels like we've been really obsessive about trying to capture each part of the hydrograph in a reliable way, it's because there's a lot of the parts of the hydrograph matter in this context. You can't just effectively match peak flows at the expense of everything else, or match base flows at the expense of everything else. The whole system has to be in balance and through the entire annual hydrograph. So with that, moving away from the overall study orientation into the hydrologic model, this is, and I'm going to, unless I'm specifically referring to the GS flow model that Santa Margarita Water District and Wildermuth developed, anytime I refer to a model, I'll be referring to the Lspc model, which is the model that's been developed as part of this study. So this model is a watershed, a hydrologic model that represents precipitation and applied water on the landscape, turns that into seepage, runoff, evapotranspiration. That runoff can enter the stream through direct inflows or through storm drains. It can also enter the stream through groundwater recession that occurs both right after a storm as well as all the way through the summertime. And once it's in the stream, it can be lost to evapotranspiration, or it can be withdrawn at specific flow diversion locations where those exist. And so through each subbasin, water gets added and subtracted and routed into downstream elements. And this is the discretization of those elements. Each of these light blue boundaries is a subbasin in the model. And what's new about this graphic is a more specific depiction of which areas of the model are being represented by the Lspc model, and those are the hollow ones where you can see the aerial photography underneath of them, and which ones are being simulated using or being represented using the output GS flow model that Santa Margarita Water District developed. Those are specifically areas that are more influenced by groundwater surface water interactions and potential pumping operations, where that model provides a better representation of those. The light gray are areas that are not included in this study. It's not that they aren't modeled hydrologically and that their inputs aren't included hydrologically. It's just that the existing flow management paradigms exist for those, and therefore they are not a subject of the investigation that SQUIRP is doing as part of flow ecology in this study. And then finally, the dark gray are these small coastal watersheds that are also not part of the not part of the study. that's sort of the end of the background on the Lspc model. But yeah, if you have an additional interest in all the features that go into this, the sort of mechanics and the inputs and so on, there's some good material. We went into this in detail back in January as well as July, and so you could either review the meeting materials, the slideshow, or view the recording. So now moving into what are we doing now? What are we presenting today? We're presenting the recalibration of the Lspc model. And I mentioned this already, that we've obtained isotope data from both outfalls and in-stream points. And we got those data back from San Diego State back in late August. And so it's been a kind of a mad rush to get those in, get them interpreted, as well as start to match those data in this model and get ready for this presentation. I don't think mad rush is quite right, but it's we've been working on this pretty intently since August to get ready to share results. Yeah, I mentioned we also had some prioritized comments from June and really focused specifically on the low flow conditions, both during winter low flows and summer low flows. We wanted to do all that and still maintain the adequate wet weather calibration that we had previously presented, moving into evaluating goodness of fit at additional places where we have some calibration data. So the isotope study we've been waiting for. This is really two scopes. One was outfall investigations. So there were various 20 outfall investigations completed in the spring and fall of 2019. And these were done through a lot of different lenses, through the lens of microbiology, through the lens of flow and flow patterns. But one of the lines of evidence that has come in more recently has been the isotope composition of these outfall flows. So these are major outfalls that drain significant urban areas. You can see the outlines on the map of the outfalls that were monitored. And so this represents both what's coming into the storm drain, kind of from the curb into the gutter, into the inlet, and then into the storm drain, as well as what seeps out of the side of slopes and natural seeps that are persistent throughout the year, and everything in between. You know, these are big watersheds, so it's not simply groundwater intrusion into the pipes that would explain groundwater in the system. It's potentially groundwater seeping out of a hill at one elevation, flowing down across the curb and into the gutter and into the system and showing up at the end. The other component of the study was in-stream points that were done more recently. They were done in March, May, and July of this year, or very late July, either late July or early August, when samples were collected. And so these also included control samples, collecting potable, reclaimed, and rainwater to evaluate their composition, and then collecting 3 samples at each of the black and red dots on this map, representing a higher density in Aliso to kind of try to understand the longitudinal profile of isotopic composition as it comes through the watershed, but at key points in a variety of other tributaries that are part of this study. One of the key elements of this is the question of how much of this water is coming from groundwater in the system versus through an overland flow pathway during dry weather. And so just wanted to spend a minute talking about the groundwater sample locations. These are not like alluvial groundwater extracted from a well in San Juan Creek. These are areas where there's flow persistently coming out the side of a slope or the side of a channel into the system. Many of them are indeed right adjacent to the channel, so they represent, you know, a valley where water is flowing down through through subsurface pathways and entering the creek just above where the creek's normal high water level is. And others are like such as this one down in Salt Creek are a little further up on a hill slope. So in any case, one of the key signatures of these is none of these are out in the wildland open space. These are all sort of groundwater that represents the current state of groundwater with the various urban influences that exist in the watershed. So with that, I just wanted, we'll get into some of the data, but to give you a preview of the findings, we found that the groundwater seeps are continuously flowing through the summer. So these are not just perched and episodic sort of groundwater. This is groundwater that's continuously flowing. It is predominantly rainwater, but it does contain a significant imported water signature. Likely pathways would be irrigation that seeps below the root zone of lawns and other vegetation that then enters the groundwater table. So we know that the groundwater is predominantly rainfall derived, but has a significant signature of imported water as well in these urbanized areas. The outfalls that were sampled range wildly. Obviously, something that is very tightly drained and predominantly from an urban area can end up with an imported water signature in the range of greater than 90%, i.e. less than 10% groundwater and other sources rainfall. But on average, what we saw was that the outfalls were around 60% groundwater. And then, so the other component of that is then the surface runoff that occurs from the watersheds due to irrigation, overspray, and other releases in the urban environment. So we saw that the ratios didn't change a lot through the duration of these studies, as samples were collected in May. I think in some of these cases collected in, say, May and then July and then August. We didn't see much change in the composition there. We saw the groundwater signature persist. We did see, obviously, as I mentioned, some outfalls, much greater groundwater contribution than others. And then on the in-stream composition, we saw this vary also in space, not to as great of a degree as we saw it vary in the outfalls. We also saw it vary in time, as you would expect. We saw some groundwater decline in between natural rainwater derived groundwater decline between the March samples and the late July samples, representing some dissipation there. So that's the preview, and now I'll show you the data that supports these conclusions. So here's a standard isotope plot. What you do is you look at the hydrogen and oxygen variance here, and the lightest water is off to the left, lower left. The heaviest version of water atoms is up to the upper right. The underlying theory here is that as water moves inland, moves up in elevation, the first stuff that falls is the heaviest. And so when you're a coastal watershed, you tend to get a lot heavier water on average isotopic signature than if you're up in the Sierra or if you're in Colorado. And so we see this bear out. We see the lightest by far grouped together in the potable water and recycled water, which are pretty similar in the lower left, coming from other places, coming from places at higher elevation and further inland. And we see the local rainwater and the groundwater trending up towards the heavier side of the spectrum, indicating locally derived. So when we, so this sort of then aligns with that finding I showed you about the groundwater being more locally rainwater derived than imported water derived. And then so when we add the outfall, so when we add the in-stream samples on this, I'm showing the in-stream samples here. We see that they range. Some of them do end up further towards the groundwater side, or sorry, towards the imported water side, and a lot of them end up more towards the groundwater side. So there's not a specific rule, but you see the color codes here by watershed. And so you do see some certain watersheds cluster together with each other. I'll get into the specific numbers. It's hard to make an assessment directly from this visual. So the first question we'll kind of come to is the data that support the finding that groundwater is about 20 to 35% imported water on average. And these are just the data there. I don't know that there's much more of a punchline than that. Outfall flow composition. So there's two different ways to look at this. You can look at it by the pathway that it took to get to the outfall. And so I'm showing all of the Aliso Creek outfalls here. And so you can see that on average in Aliso Creek, about 70% of water got to the outfall via a groundwater pathway, and that about 30% is explained by dry weather runoff directly from potable water. When you think about origin, it skews it more 50-50 because groundwater is partly imported and partly rainfall derived. And so now this is splitting it by what came from local rainfall and what came from imported water. And so that's about a 50-50 split in Aliso, and it varies by outfall considerably. And here's another look at this, mostly for your reference purposes later, of how this looks in other watersheds. Oso looks pretty similar to Aliso, and then various other watersheds have differences. So now the next question, this is a new question, which is what do we see in the streams? Not all the water that's in the streams came from the outfall. There's water that comes to the streams directly from seeps and springs and other sources that that aren't captured in the outfall data. And so this is a look across all of the monitoring locations at how things look overall, and then how they changed from March to July. And so we do see some variability. The more watersheds that have a greater amount of preserved open space in them, Trabuco and Laguna Canyon, tend to have some of the lowest imported water fractions. A lot of the watersheds that are more urbanized are fairly similar in the sort of mid-20s to low 30s range. One of the things that I think is a clear signal here is that we do see a consistent shift towards a greater percentage of imported water between March and July, further away from the wet season. This is a shift, a significant one. What I would also say is that this is not a dramatic overall categorical shift. I think in our previous assessment of this, we looked at this a lot through the lens of it's mostly imported water supplying the creeks in the summertime. And so a much more significant shift. And what the data here suggests is that it's a gradual shift, but not one that that goes completely to imported water in the summertime. And here's a little closer look at Aliso from moving from top to bottom. We didn't really see a significant longitudinal profile as we move from up in the watershed to the bottom of the watershed. One point to note here from an interpretation, and we'll come back to this in the calibration, is that of the 3.7 CFS or so that were flowing in Aliso Creek in July of this year, these data suggest that about 2.7 of that were derived from local rainfall. So we'll come back to that, but I think it's a relatively significant finding as we think about what it might have looked like in a reference condition, and also how how water conservation and how climate change could potentially impact these values. So these are the same general findings, but now moving into modeling implications, and I suppose if there's, we don't have a signpost here, but we have just presented a lot of data, and we've kind of reached a point where we're going to transition from isotope study into the model. And so if there are any comments or questions that folks would like to get off their chest right now, I'd be glad to pause here. I think we probably owed people a pause for comments.
Hey, Aaron,
a little earlier here.
Hi, Aaron, this is Cindy. I know Christine Medic had her hand raised for the isotope during the isotope slide. So Christine, did you have a question?
Well, it's not a real burning question. You started talking about, so isotope, this is new to me, so I just had a general interest question about when you're talking about heavy versus light water. Are you talking about like the amount of salts or other solids in the water, or what does that mean exactly?
No, not at all. When water evaporates off the ocean, it is effectively pure water. This is about the and I'm not an isotope scientist, and so I probably will butcher this a little bit, Christine. I'm sorry, but it has to do with the ratios of hydrogen 18 versus hydrogen 16. You know, kind of like when you look at carbon dating things, you're looking at ratios of different carbon isotopes, carbon. I don't know those either, the numbers, but there are different actual atomic arrangements of electrons and protons that and neutrons that cause certain atoms to be heavier versions of, say, oxygen and heavier versions of hydrogen. And so what happens when water condenses then in clouds is that the heaviest ones have a tendency to come out first by virtue of the physics. The atomic physics of it, and that means that the first water that comes out of a cloud after it starts to condense are going to tend to be the heaviest ones, and then as it moves over land and it moves up higher in elevation and it becomes more expended, then the latest the last stuff to come out of the cloud is going to be the lightest molecules and atoms. Does that answer your question?
And so the assumption is that water that's been imported is lighter because it's been on the ground longer?
The water that's imported is lighter because it fell in a location that was much further inland and at higher elevations, so that by the time the water reaches the Sierra, on average, more of the heavy molecules have already fallen on coastal and inland California, or in the case of Colorado, even a much greater area, and so that the water that fell there, which then becomes the water that gets imported, is lighter when it fell. It's a lighter isotopic signature when it fell.
Okay, thanks for that.
Yeah. And we see it. We see. I mean, if you were importing your water from just down the road, you might not see enough of a difference in the data to be able to use these methods. But since we, go back to this slide, since we see our local rainwater signature and our local groundwater all the way over here on the spectrum, and we see our imported water all the way down here on the spectrum, it gives a pretty good amount of resolution. Probably we shouldn't be interpreting this down to the single percent, but in kind of 10%, 15% ranges, this is enough of a resolution to be able to use these methods to understand the overall origin of water. All right. So, are there any other questions?
Yeah, so there are a few chats and then a few raised hands. So let's go through Lindsay Stuvik in the chat. She says, let's see, we received 4 inches of rainfall in March this year, which could affect the overall percentage of imported water relative to July. Is there any consideration of looking at the percentage of imported water in May 2020 when we didn't have any rainfall?
Yeah. We saw a similar shift from May, although I would say that we planned the March sampling events so that they represented base flow The study design included not sampling right after rainfall, so gave it about I think we gave it about a week or two since the end of rainfall in March before samples were collected. So yes, it does represent rainfall influence, and that is in part, well, that was effectively by design, is that we wanted to understand what does base flow look like in a month like March, which is fairly soon after rainfall, and in obviously the end of July when there hasn't been rainfall in several months, at least a few months. And then I see Amber's question, providing a technical report to comment on. We will be, when it comes to the we are documenting the study. That's something we will be doing in the next month and a half as we reach the end of December. So there will be documentation of the study. I think that's the simple answer to that question.
Okay, and then we have two individuals that have their hand raised. So we have Charles Weslinger. So Charles?
Yeah, can you hear me?
Yes, we can hear you, Charles.
Yeah. Hey, Aaron. So real quick, going back to this lighter versus heavier water, I just wanted to make sure, because obviously when we talk about Colorado River water, that makes complete sense in what you talked about. But my question is when we talk about blending of imported water, particularly water coming from the Bay Area, and now remember that this blending is also dependent upon what the allocation is on the state water project in times of the year, and then also how Met is blending the different types of water between Colorado River and Bay Area water coming off the state water project. Does this change that analysis? I just want to make sure we're not going down some assumptions that could be influenced by some other factors.
The short answer, Charles, is the differences you're noting could very well explain the minor variation we're seeing in the samples that were collected from potable water in the watersheds. There is some difference, over the course of the studies as to what what potable water has looked like in the region. So, yes, there is no way to derive this in theory, quote unquote. We can't just say X% came from the Sierra, X% came from Colorado, and therefore our composition is this. We have to take local end member samples. These are basically control samples to inform how you interpret the study. So if we were to go out again in 3 years, we would not reuse these samples. We would go collect new ones to say, okay, what does potable water look like right now? So the theory is that, why there are differences is the theory I described, but the actual differences we're seeing are based on measurement that we're collecting here. So you can think about these more as a conservative tracer, so to speak, in a study where you've collected the samples of the known potential contributors and then use those to interpret those mixed samples in the middle.
Okay, thank you.
But it's a good point that we should never, you really shouldn't do these based on theory, because different storms bring different isotopic concentrations. One that starts way out off the Pacific may have dropped all of its light water before it gets to Orange County, or heavier water, and you may see a lighter signature then. So you really have to use the control samples of the actual water, the groundwater, the potable water that represents the integration of long-term conditions. So I'll stop on that, except to say that this is the study design here. I think is reliable to distinguish these sources. So I have a couple of comments. I think Cindy, I guess maybe somebody else had their hand up, or should we go back to the comment panel?
Mike Beenan had his hand up as well. Mike? I think you're still muted, Mike, if you wanted to unmute yourself and ask Aaron your question. Okay, maybe we can come back to Mike.
Okay.
Here we go. I found it. I
He's
think.
here.
Okay, there you go. Okay.
Yeah, sorry about that. I'm still learning to navigate this. Thanks so
Okay.
much. I think it's great you're applying this high level of science. We've always been promoting sound science. You indicated July the 3.7 CFS, 2.7 CFS from rainwater. Previous EIRs at the coastal treatment plant found a flow rate of 1.5 CFS. And in looking at the July Orange County flow data, it looks like you have midday spikes occurring every day, almost double the flow in the creek. So I'm not sure how we got to the 3.7 CFS and calling it 2.7 rainwater. And then the other part of my concern is the MS4 permit is responsible for regulated coastal receiving waters. And SQUIRP and others can define the plume, actually using some of these metrics that you're using. So I would encourage, once again, that for a fully integrated watershed model, that we indicate the size and extent of the coastal plume, particularly during dry weather flows. Thank you.
I take a note of those questions, Mike, or comments, Mike.
Thank you.
Okay, I saw somebody else had their hand raised, but they've lowered it now. If that was an accident, please raise your hand again. But there are a few more things in the chat. Let's see.
I think Cindy's responded. I guess I'd augment Cindy's response by saying that we don't have the luxury of having a technical report out for the hydrologic modeling for a full review before we perform the flow ecology synthesis, and so that work really needs to get started. And so we're hoping we thank you for your patience to comment on a presentation format and to let us know if there are any big picture concerns that significantly influence the reliability of these results to be used in the flow ecology analysis. It's the goal of today, and there will also be an opportunity to comment on the technical report.
Yes, and then I see Amber had a question about elaborating on the use of rainwater control in the 20 in-stream points. Are you saying that you used a calibrated set of isotopes for the rainwater control for the data set in July and August of 2020?
We, for the rainwater control, we have, so I also say that all the isotope analysis is being summarized in a report being prepared by Dr. Chantal Lai at San Diego State University. So it'll be a third-party technical report that complements the special study and outline all the isotope methods and the method of interpretation. One of the methods of interpretation being used in that is an additional set of rainwater samples that San Diego State has collected on behalf of themselves as well as other clients around the Southern California area. And so the rainwater end member is coming from a combination of rainwater collected over the last 5 years or so, representing what he believes to be the average rainwater signature across multiple storms and over space in this local region. So that's the basis for that rainwater end member. It goes beyond simply the 3 samples we were able to collect during this study. It includes a larger data set that he's collected over time.
Thank you, Aaron. We have another question from Lucy. Do you expect that these field data informed modeling results are extrapolable, interpolatable year to year, or given the natural and managed hydrologic variability, there is some interannual variability to reckon with? General question about the temporal bounds of the fieldwork here, especially in anticipation of climate change scenario analysis. Thank you.
Lucy, that's a great question. That is still a limitation of this study, is that we do have the isotope data at a certain spot in time, basically over 2 years between 2019 and 2020. Thankfully, those 2 years don't correspond to like a very, very anomalous condition like what we saw between 2012 and 2015. And so we do have a sense that they're probably closer to a long-term average condition and aren't terribly skewed by drought. But that said, I would be conjecturing to say that they represent actual long-term averages, and I would also be conjecturing to say that they are that we know exactly how they vary over time. We do know that that the winters that preceded these sampling events were not exceptionally wet or exceptionally dry, and so that we, from a long-term average sense, it's these are probably pretty realistic data. So but in terms of exactly how how this system would respond to a prolonged drought, in terms of what we would have seen had we done an isotope sample in 2015 at the end of 4 years of drought, that it's hard to tell. So we've used these to calibrate the hydrologic model for this most recent period that represents kind of post-drought normals in terms of people's water usage as well as rainfall, and we've looked at those, and then we can use the model to extrapolate backwards as to what things would be in under different climatic periods, as well as what they may be moving into the future for climate change.
Awesome. Lucy says, gotcha, thanks. Helpful context. Our evolving non-stationarity is tricky.
Absolutely.
Let's see.
It definitely is. Thanks for understanding that.
So Amber followed up asking about the isotope study from SDSU, asking if that could be distributed to the group before support comments on the presentation from Dr. Lai.
Hi, Amanda. I just replied to that. And so we're planning on submitting that report from Dr. Lai with our WQIP annual report, and then that will be made available for review through the South Orange County Regional Clearinghouse after January 31st. So it'll be available for review then.
Wonderful. And then let's see, Jim Burr asked, is there a reason a draft report wasn't released before this presentation? It's hard to fully understand this technical presentation without an opportunity to review a report. This is particularly true since scenarios were determined without much input from stakeholder groups. How are any new potential scenarios recommended from the stakeholders to be included and or assessed? Yes, and then Christine asked about something else as well. But we can respond to Jim first. Maybe it'd be helpful to kind of go through the kind of timeline of review and what we're looking for from this meeting, and what we'll be distributing throughout the next few months.
Yeah, I think that's good. I think I'm sensing that there's a lot of comments hinge on the ability to, maybe not the technical comment being presented right now, but the ability to review and to provide comments on this in a different format. And I totally understand that concern. And I want to revisit the purpose of the meeting is to get your initial feedback on this and to identify areas of specific concern. Obviously, this is compressed. The main reason why the report hasn't been published was, of course, we got some of this really critical data right at the end of August, and it takes time to incorporate the data into a model. Models, we achieved a calibration that we're really happy with, that Rich will present next, last week, and the week before in different parts of the watershed. And so there's, we really want to hit this with you and get your feedback early. We're trying to hit an end of year milestone to have at least the special study portion of this study complete, and also recognize that as comments come in, as additional scenarios are identified, this is just the foundation for additional evolution of this program and additional refinement of tools and data sets that will come after the end of this year. So we have sort of we have some time pressure at this point to produce the draft of this study, showing you how, the documentation of the modeling as well as the documentation of the flow ecology portion and how it all comes together. It will be a draft, and certainly as there are opportunity for you to review that in whole and comment and identify additional scenarios or identify additional refinements, those will be considered as we move forward and think about what the future of this program has to hold. So it's a bit of a phasing. I mean, we are trying to wrap up what could be called phase 1 and produce full draft results, but without any sense that this will be the end of the story and the end of opportunity to comment on this. So I hope to alleviate some of the concern and some of the pressure that you feel right now to comment now or forever hold your peace, and that's not what we're trying to imply. But we do want to bring you along with the substantial updates to the modeling and give you a chance to comment and identify areas of concern before we expend additional effort on the ecological analysis. So I don't know, Cindy or Grant, if you have anything to add to that in terms of expectation setting. I realize we didn't come to that all that well right up front to help you understand where we sit in the process, and I can understand some of the concern you're expressing about lack of ability to comment on a detailed technical report yet.
I don't have anything else to add, Aaron. I think you summed it up pretty well. I think the original study intent that's been laid out within the WQIP and what we are doing currently and what Aaron, his team, as well as the SQUIRT team are going to be presenting on has somewhat diverged, and if not, has blossomed into something a little bit bigger than what we had intended for this special study. And so we are listening to all the comments and taking into consideration all the comments and the approach for the study based on these stakeholder interactions. And so, so a lot of what will be inputted into the technical memo that will be submitted are based on what has already been presented or has been provided through comments through the stakeholder approach. And so, so there are concerns about what will be presented. We are asking that folks address that through the stakeholder process. And so that's kind of a rationale why we're not planning on, submitting a memo or anything like that for review, because a lot of the comments that have been provided through the stakeholder process has been addressed through the stakeholder through these various workshops, and so that we ask that we continue on through this process to accept comments. So hopefully that helps and provides additional clarification on that. I don't know if you wanted to add anything to that, Grant.
No, I don't have anything specific to add. I think both you and Aaron have provided good explanation. But I will circle back to what Aaron said is absolutely correct, that we're looking at the commitments within the water quality improvement plan for South Orange County. They're such that we will be providing some deliverables at the end of this year or the end of January, as Cindy said, when the annual report is submitted. But it by no means is the end of this effort, nor does it signify the end of when we would consider comments and feedback on the data products coming out of this. So we're not looking at it as necessarily the end of this special study, because the data that's driving this is only going to improve with time, and our ability to understand it and interpret it coming out of this is only going to improve. So we welcome your comments and feedback at any point along the way here.
All right. Okay, so I'm gonna spin back up into presenting technical information, and I thank you for your patience in seeing this for the first time, or having maybe only seen it since Monday, and in presentation format. But we'll try to be clear about what we did, and hopefully to explain it well enough to elicit your feedback now today, if you have any. Based on our findings, what does this mean for the model that then drives different scenarios? We previously had a lot of the water at the MS4 outfalls being derived from imported water directly from irrigation overspray. We see that quite a bit of that comes through groundwater pathways, and quite a bit of that groundwater is rainwater derived. So that definitely changes the hydrologic processes that we think dominate in this watershed, and shifts those. In terms of the in-stream samples that we saw, same type of trajectory. It tells us that we should be increasing the importance of rainfall-derived recharge in the model, and reducing the importance of irrigation overspray to match the data we're seeing. And that one of the things that we see from this is that it's pretty likely that dry season base flow is present in this in some years, or a lot of years, in the absence of urban influences, which is pretty different than, if you remember, what we talked about last time. And then that's absolutely mea culpa in terms of having new data and really changing your worldview around the system. And that's what you'll see here. So with this, before I hand off to Rich, we use these to establish a whole new category of calibration targets. We still have the flow data that we're matching both for base flow and for peak flows and everything in between, but we've identified some additional targets, being including how much of the groundwater recharge is happening in the model is coming during dry periods, i.e. with based on irrigation overspray and seepage, excess irrigation is seeping below the root zone, and how much is coming through rainfall-derived recharge. How much we originally already were calibrating to how much flow is coming from dry weather areas, but we now realize that a lot of the flow that's coming out of the pipes in these developed areas during dry weather is coming from groundwater discharge, and a portion of it is coming from surface discharge. And so that that changes sort of how we apply the irrigation in the model and how we simulate these different processes. Qualitatively, we see that active groundwater discharge continues through the summertime instead of going to zero in the summertime. And we, as I mentioned, stream flow composition becomes a target that we can evaluate based on the model. We can look at how much water is coming from groundwater, what the composition of that groundwater is, as well as what's coming from overspray, and what's coming from unimpacted parts of the watershed where you wouldn't expect any imported water in the groundwater. And you can bring those all together from the model to look at whether we are fairly close to the isotope compositions we saw in the monitoring data. So I'm gonna hand off to Rich, and to introduce Rich. Rich is our lead modeler for Lspc, and has been doing a heavy lift on these data and the model scenarios since we got them back in August. So I'm gonna hand it off to Rich to talk about how we did this, what we found, and what our model performance looks like.
Hi, everybody. My name is Rich. It's a pleasure to be presenting to you today, and thanks, Aaron, for the handoff. So essentially, as Aaron just said, we had the existing constraints that the model needed to conform to. Like, one example would be the irrigation water volume. However, another important constraint is the isotope data and the percentage of imported water that needed to be reflected in the model. And so we made some significant adjustments to the model calibration to accommodate that. Here they are. We needed to reconfigure the balance between applied water and evapotranspiration demand, and that involved changing the irrigation volume just a little bit, well, certainly within range of the possible volumes that are indicated by the data we received from the Moulton Miguel Water District. And some of the deeper details of the model actually relate to how infiltrating water passes through the root zone, what an appropriate thickness for the root zone might be, and what infiltration parameters look like for the soil. And then once water has percolated and infiltrated into the aquifer material, how rapidly is it released as groundwater discharge to stream channels? So these are the general things we thought about as we were doing this. And Aaron, let's move to the next slide. Okay, great, thanks. So we thought this through. We developed new calibration targets, and we needed to have our groundwater discharge to the stream channel during dry weather be composed of a much lower fraction of imported water. Our target was 20 to 35%, and so our result in this new calibration we achieved is 28%. So check, that's a good one. We had total dry weather flow from developed areas maintained at 3 times 10 to the negative 4 CFS per acre in developed subbasins, and dry weather surface runoff maintained at 1 times 10 to the negative 4 CFS per developed acre in developed subbasins. We had those constraints met before, and essentially we needed to perturb them to accommodate the dry weather groundwater recharge and then get back to them through readjusting some other parameters in the model. We needed to watch our groundwater discharge carefully. This continues through the summer and declines between spring and summer. This was not necessarily something we had to focus on in such detail earlier this year because our summertime stream flows were supported by irrigation water runoff. Well, now, if irrigation water needs to make up a lower fraction of the stream flow, that means we needed to pay much more careful attention to the contributions of groundwater discharge from groundwater that infiltrated during rainy times, but discharging in the dry weather times in the summer to support base flow then. And then stream flow composition should be in the 25 to 35% range in the Aliso watershed. Sorry, stream flow composition should be composed 25 to 35% of imported water, and then the remainder from rainwater that fell that fell in the wintertime. And the result in the model is 32%, so we're within that range as well. Aaron, let's move on to the next slide, please. Aaron is muted. Aaron has a circle that is going around. Now we have faded text.
Oh,
We're
no.
in suspense.
Oh no. Our circle has left us, and now we are trying to advance. Okay.
Okay, great. Here we are. So, so this is a sort of a funny graph. What you're seeing is not quite 5, about 4.5 years on the horizontal axis. And we're plotting flow in Aliso Creek at the sewage treatment plant gauge. Let's
Yeah. That was the circly thing. It was delaying my
okay.
my advance, and now it has it received my advance, and now it wants to go non-responsive again. I apologize, Rich. It's not a very nice thing to do to you. Let me see if I can get it. Let me see if I can get it back to being responsive to me again.
We can blame the Microsoft Corporation or some internet service provider somewhere.
All right. I think we have a delayed advance now, and we probably will go back. Oh my gosh. This is where patience comes in handy. Don't know why this is happening.
I will.
I think what I may do is stop sharing my screen and start sharing it again, and
yeah,
see
sure.
see if we can go ahead and resolve the.
I can give a
the team's lag.
Yeah, sure. What we're going to see when Aaron brings this up is we're going to be trying to show you the agreement between model output and measured data at the gauge that is at the sewage treatment plant location on Aliso Creek. And there's also what we refer to as wading flows. These are flows measured by Orange County Public Works staff members who physically wade into the stream and measure the depth of the water and use a rating table to estimate flow. And so these are two separate ways of assessing the flow rate. Wading flows are useful because they are not subject to sensor drift. We haven't had too much problem with that at the ALISO at STP gauge. There's a couple other locations where sensors can be perturbed by debris coming downstream. And so it's handy to have the wading flows as well as a double check for flows. And
Rich, I'm going to be able to share again real soon. I don't know what happened, but I'm going to give it another try, and hopefully we'll be back to have an audio visual together. So, you can. Thanks everyone for your patience.
I think it's page 32 of the slides. No, around there, 31.
Yeah, you're on.
Just
you're
follow
on 30
along while you're resolving.
Yeah, thank you.
That's a good point. The slides have been updated on the website, and so if you get to the meeting materials through there, you'll see the slides that we're currently using.
Yeah, all right. So now let me try to.
We would definitely not know we were in 2020 if we didn't have a nice tech glitch on a meeting.
All right. Well, we're almost there on the screen share as well. We need to go back one slide, Aaron.
Sure. Not sure why things continue to lag though for me.
All right.
We can follow along with the slides if you want to just direct us to those, should you have future issues.
Thank you.
Yeah, that sounds good.
All right. Hopefully everybody's able to see the slides again.
Okay. So on the horizontal axis, we have time going from, in this case, October 2015 to October 2017. We have the wading flows in the lower panel are the gray diamonds. You can see them interspersed throughout. And model output is in orange, observed flow from the gauge is in blue. And we have the flow on the vertical axis. You might ask, why does it look so strange? Why are there all these vertical lines here in the orange and the blue? We actually are so zoomed in on the vertical axis because we're trying to look at the low flows, because these are of greatest interest for the flow ecology study, that the vertical lines are actually higher flow events when it rains and the flow shooting up to flows greater than 20 CFS. So that's normal, that's not a problem. And if you're looking at this and you're shrugging your shoulders and saying, what's the big deal? The orange and the blue are on top of each other in the top panel, and the orange and the blue are on top of each other in the bottom panel. That's the good news. That means that in both cases, the model output matches the data, but the idea is in the lower panel, in the new calibration, we have that occurring while meeting the other constraints we were discussing earlier, most notably the constraint that is placed upon us by the isotope data to not have more than about 30% imported water in the stream flow, even in the summertime. Yeah. And then the other bonus here is that you can actually see that the fit between orange and blue in the lower panel, the new calibration, is a little bit better than in the upper panel, especially in the wet winter of 2016-2017, where you can see when the blue line comes down, the orange line doesn't quite come down quite as much in the upper panel, but that is actually fixed in the lower panel. So that's quite nice, actually, that matching the isotope data actually led to improvements in other nuanced dimensions of the calibration. Aaron, let's go ahead to the next slide. Right, okay, so these are the takeaways. We had a calibration, we perturbed it to incorporate the information given to us by the isotope data, and then we re-established the calibration. And so we have a significant shift toward rainfall-derived seepage and away from irrigation-derived runoff, especially insofar as the source of summertime base flow. Let's move on, Aaron. Do we have any questions, any thoughts in that section of the talk? This concept of how the data led to new calibration targets and whether we met them. I see.
Yes, we have a chat from Christine. Is the model still underestimating dry flow? Blue line below orange. If we go back.
Not significantly at LISO at STP. In fact, and I can tell you just off the top of my head, for other locations, we don't have significant, we're going to keep going with this topic. So hold that thought, Christine, but the answer is maybe a tiny bit on some days, but it's not that meaningful overall through the simulation. We have more assessments of the current conditions calibration coming up in just a second.
And then Mike Beenan also has his hand raised. Right?
Yeah.
Yes. Well, first of all, thank you. It does my soul good to see you struggling sometimes with the technology. So thank you for reassuring us. It's not just us. On the how do we go about separating the groundwater from a rain contribution versus irrigation seepage to the groundwater? Because we have inland golf courses that irrigate pretty heavy. That would cause seepage, and the seepage would migrate out and maybe be read as groundwater. So is the testing sophisticated enough to separate seepage from irrigation water into groundwater?
Now, Mike, let me just make sure I understand your question precisely. Are you asking how we do this when we're looking at the model results, or are you asking about this for like real life data?
Well, I guess both, because as I said earlier, July from the Orange County Public Works shows daily spikes, significant spikes in the middle of the day, indicating irrigation water is getting into the creek. It doesn't indicate how it got there. And I'm wondering, when we look at groundwater seepage, both in the model and monitoring, do we have tests that can separate out irrigation-derived groundwater versus rain-derived groundwater?
Yeah, I'll go ahead and come back to the earlier discussion.
Yeah.
Yeah, the earlier discussion we had on the isotope data is that yes, we are able to look at the groundwater seeps that were collected, and these, I mean, notably, Mike, these are not often the in the Cleveland National Forest type of groundwater seeps. These are right there adjacent to development, where if there was influence from seepage, you would see it in the from imported water, you would see it in the groundwater seeps. And in fact, we do see it in the groundwater seeps. We see it, imported water contributing anywhere between about 20 and 35% of the water that's at the that's seeping, coming from irrigation excess. And it's hard to water a lawn without letting a little go beyond the root zone, and so that kind of inefficiency that leads to some seepage from imported water is pretty common. It's very it's very common in agriculture. It's common in any kind of irrigation application, and so we see it, we quantify it, and that is part of the analysis, and so that. Yes, so some of the imported water that's getting into the creek is coming through groundwater seepage and out of groundwater discharges, and some of it's coming from irrigation overspray. And we've represented the same type of processes and mix of processes in the model.
So thank you, Aaron. So just so I'm clear, so the model and the field work is sophisticated enough to separate out within the groundwater sources that are rainwater versus sources that are either imported or reclaimed that get into the groundwater seepage.
Yes.
Okay, thank you so much. Thanks for clarifying.
That is a simple summary. Yep.
Thank you.
Let's see who's next in the hand raise. I see Roger Buteau. Go ahead and unmute yourself, Roger, and then you can say your question.
Hey, can you hear me now?
I do hear you now. Go ahead.
Okay, 5 by 5.
I'm not sure what that means, but go ahead.
I think it's an old military term. It means I hear you loud and clear.
Yeah. Okay, then 5 by 5.
Yeah, I see you learned something today. Stick around, right, Aaron? You always learn something around me, don't you? Okay, my question is this. Molten Miguel Water District received, I believe, some kind of a grant, either from Met, I think it was from Met or from MODOC. They did not only test wells, I know because I looked at all of the literature, except I never saw the results. So the question is this: the data that Molten Miguel acquired, which involved not only drilling, I think, several wells up around I would call it the middle reach, from the lower to the middle reach within their service district. They drilled several wells, I believe it was a year or two ago. They also did some surface monitoring. Is that data integrated into your work?
I would say not directly, Michael, or sorry, Roger.
Believe me, don't ever confuse me with Michael Beenan.
You got me.
Okay.
Sorry, Roger. Those data were that report. And I'm forgetting the firm that developed it. I should have that off the top of my head. But I know exactly what you're referring to. They drilled some test wells in the alluvial aquifer in Aliso Creek in the midsection, yeah, near Aliso Viejo Park, there along the creek, and they characterized the amount of potential sustainable yield of the system there. And they were focused specifically on what's flowing through the a little bit more permeable layer that exists between about, if I had to get, I think it's about 40 feet down as the bottom and maybe 15 feet down as the top. So there's sort of a bit of a confined space there that transports some water, characterize the water quality of it and the flow rate of it based on some simple methods, looking at permeability. And the primary assessment there was how much water could we potentially pull out of this system. And I think the general conclusion that it found that informs the study a bit is that there's not a ton of water flowing subsurface below Aliso Creek, which I think is what a lot of people have known. It doesn't have a big alluvial aquifer system like San Juan Creek and Trabuco Creek have in terms of transporting a lot of water. And so that is one data point. I would say that water entering the creek is not that's represented in the model in groundwater flow in the creek is not entirely coming from that source. It's not water that gets into this alluvial aquifer that runs along this ribbon of the creek down the system. But it's partly that. It could also be, and likely is partly, seeps that come in laterally from above that elevation. So groundwater table sloping up into the hills on both sides of the creek. Water moving from that groundwater into the creek directly. So it's an apples to oranges comparison. That was an assessment in a focused area to assess the question of how much water could we potentially pull out. But it was not an assessment of the overall pathways for groundwater to get into the system in the thinking of the overall watershed. So it wasn't something that was directly useful. The isotope studies were, I think, a lot more direct to the questions that were are relevant to us and we're asking as part of this this project.
Can I ask a follow-up question, please, Aaron?
You may.
So do you or do you not have all of the data that Molten Miguel procured with grant funding, by the way? Do you or do you not have that database? And if so, how do we get a hold of it? To my knowledge, it's never been publicized. Basically, my group, Clean Water Now, would like that information without having to go through a Public Record Act request, especially considering that public grant money was used to procure the data. It seems to me I shouldn't have to jump through hoops to get that information. So I guess it's a two-part follow-up. Number one,
I think the simple answer, Roger, is yes, we can provide that report. We've gotten it from Molten Miguel, and I've gotten permission from Molten Miguel that there's nothing about it that can't be shared. It was something, if you recall the Aliso Creek white papers that were being developed earlier and will be released soon. It's something that was summarized in that, and and it will be posted for everyone to have access to. So I think the answer to both of those is yes and yes, although there are no data from that specifically that result in model inputs for us, so that we have them, but we don't have a use for them in a direct data way, only from a more of a broader sense of understanding the watershed way.
Okay, if you see where I'm going, we as NGO reps should not have to constantly fill out Public Record Act requests for data, once again, that was acquired with public funds. It seems kind of almost obscene that we have to keep filing paperwork that is absolutely a waste of not only the staff time of the agency, but also those of us that are all volunteer organizations. So I don't know why Molten Miguel never shared the information, but you claim you have the whole, all of it, the robust database that was acquired. I'm good with that as long as I can procure it as soon as possible. Thank you.
I have the study report that summarizes.
See,
yes.
it may not affect your modeling, Aaron, but it is important data. And once again, I tracked that. I went to the Molten Miguel meeting when they announced the procurement of the money and the launch of that testing, and then it just goes into kind of this mushroom black hole status, and then we have to actually jump. Once again, I don't think we should have to keep filing paperwork because it just eats up staff time, eats up our time. And it's, as far as I'm concerned, it's like the Brown Act. People need to be informed. Government is an instrument of the people, not the other way around. And I find it ironic that the people that are our instrument act like they are our superiors or masters or something and hoard data. That's my main gripe, has been for a long time. And for those of you that didn't know it, I can document it. Clean Water Now asks for isotopic testing. 20 years ago, we're the only ones that progressed the 13225 directive. We wanted isotopic testing to take place. So I'm glad to see it's finally happening. But hello, that was 20 years ago, and we constantly badgered both the regional board and the county public works. Why don't you do that so you can do some form of a separation test? And now we're getting the results. And by the way, I'm actually very pleased by the results. So, and I'm happy to be able to have that kind of data. But it shouldn't take, well, here we go, 20 years to get data. That testing should have taken place many, many years ago, but I guess better late than never. Out.
Right, okay, well.
Thank you for your comments, Roger.
Aaron, let's move on to the next slide because I don't see any further hands up.
We do have two questions in the chat.
Okay, go ahead, Amanda.
Yeah, it's really quick. Norman Johns from DWR is asking if we could provide some stats on performance, such as the root mean square error. He said, "Great work on the model calibration."
We will.
That's coming up as soon as we move on.
Perfect. And then Amber was asking about, let's see, slide 28, low flow AC during dry weather. She said the newly calibrated data looks better, so good job on tightening the data. The larger swings in the modeled versus observed seem to be resolved, but the smaller deviation, less than about 3 to 4 CFS, still look like it needs work. What I am wondering is what your strategies are for the dry season base flows on a potential updated calibration, potentially related to what Grant referenced in the future. And she's referring to that slide 28, low flow AC during dry weather.
We'll come back to that, Amber. I think we need to look at how this actually means, what this actually means relative to the flow ecology work, and I think we can prioritize model improvements based on that. I do think Rich would second me in the sense that there's a lot of factors that go into this. It's not as simple as just adjusting one knob and getting it there. You have to balance the whole system, and so ongoing refinement is costly, and meeting something somewhere might get you out of whack somewhere else. And so we need to, I think we're trying to assess this from a perspective of, is it good enough, not is it perfect? And so I think we can try to make that assessment again later. And I can't guarantee that there's justification to continue to make it more perfect. It's not perfect at all right now. Sorry, that was the wrong term. to make it.
No, you guys are doing good. Yeah, it's getting tighter. So that's all. I was just kind of those low flow conditions. I think are really important as they fold into the larger network.
I totally agree, and it's been our emphasis. We've had to thread a needle through a lot of different constraints, and there's I think it's much better, and better than what the data would suggest in terms of flow match, because of our much more reliable understanding of where the flow is coming from. So yeah, so I appreciate your patience, and I do think we'll identify if an improvement is really kind of important for management actions, or if it's not, and then we can come back to making plans for that.
Yeah, and we have statistical assessments of the low flow bias coming up.
Awesome, thank you.
Yes,
Helen
so
Yu is
Aaron.
asking, go ahead.
Oh no, Amanda, if there's another question, let's hear it.
Yes, there's one more. To further Mike's question, she says, I think what was done is using the isotope signature of rainwater and the isotope signature of imported water in an end member analysis to calculate the percentages from rain infiltrated water and irrigation infiltrated water. Is my understanding correct?
Yes, we used those end members to determine in specific stream samples how much of that stream sample was comprised of rainwater versus irrigation water. And then that became a constraint that the model calibration needed to meet. Previously, the summertime low flows were composed mostly of irrigation water, and the isotope information showed us that they need to actually be about 30% irrigation water and 70% rainwater that fell during the previous wet season and percolated through the aquifer and discharged to the stream channel in the summertime. So that's what the model does now. And accommodating this new constraint was the main goal of this recalibration exercise.
Wonderful, thank you. No more questions.
All right.
So to the model performance under existing conditions. We'll do this first, and then scenarios come after this. We are focusing on gauge locations when we are comparing model output to data, and the gauge locations are in these specific locations. We are only focusing on Lower Oso near Greenbridge, Aliso at Geronimo, and Aliso at STP, with Aliso at STP being the most important. The San Juan gauge and the Trabuco gauge are useful for comparison to the Santa Margarita Water District model, which is modeling that part of the watershed. So there's multiple calibration targets that we used in addition to the visual assessment of the time series plot that we showed earlier. The Nash-Sutcliffe efficiency examines the magnitude of the variance due to noise relative to the variance due to expected variation in the time series. This can be done on logarithmic data as well. Then there's the root mean squared error, but in addition to the root mean squared error that was discussed earlier in one of the comments, there's the root mean squared error relative to the standard deviation of the measured data, because it's one thing to have error, but if the error is there but small relative to the variation that is systematic and meaningful in the data, then that's okay. And then percent bias is whether the simulated data are biased positive, or sorry, not the simulated data, but whether the model output is biased positive or negative relative to the observed data. And so in the box on the right-hand side, we see the goals for each of these calibration metrics. Here is what we call a cross plot, the average flow rate in cubic feet per second measured at the gauge is on the horizontal axis, and that flow rate coming out of the computer simulation in the model output is on the vertical axis. So if a point is above the one-to-one line, the model is over-predicting, and if it's below the one-to-one line, then the model's under-predicting. You won't be surprised to hear we want the points to be on the line. The left-hand panel is monthly averages over the months for the 5 years that were simulated. The right-hand panel is daily averages. This is what we had previously. You've seen these plots already, and we were showing that we broke out our bias by different ranges of flow measured at the gauge. And so we were a little high in some of the lowest flows, and then a little, I'm sorry, let me take that back. We were a little low with negative bias in some of the lowest flows and a little high in some of the upper flows. And the overall bias was okay, but when we zoom into this level, you know, it's okay. It's less than the 25% goal we stated. But if we can go to the next slide, we'll see that we actually improve upon this now. So now the bias in flows less than 10 CFS is actually less than 1%. We're pleased about that. The bias is still the most difficult to resolve in the range of flows between 10 and 100 CFS, and then we're pretty close in the upper flows as well. And we understand that getting the lowest flows with no bias is the most important step for the flow ecology assessments that are coming up soon. So we have the previous in the gray and the new calibration in the black, and we see that we are meeting all of these calibration targets that we were aiming for. And so the 4.1 bias did not appear on the previous slide. It's the number for the overall comparison of daily average model output versus daily average data at the gauge.
Yeah, and one thing I'll note is that the log normal it puts more weight on the low flows. By reducing the importance of the high flows, just any log statistics going to better reconcile things across ranges, and so the NSC for the average in the arithmetic space is more weighted by how well we match the peak, the larger flows. The log normal highlights the lower flows more, and so we, you can see that that's the biggest improvement we saw in the model. It's going from that 0.73 last time to 0.89 this time for our match of lower, of the log.
This is a comparison of the simulation time that we use for model calibration on the left-hand side, which goes for October 1st, 2014 through May 20th, 2019. And then on the right-hand side, it is a longer simulation going from October 1st, 1993 to May 20th, 2019. You see some more triangles appearing to the right or below the one-to-one line in the right-hand panel. And that means the model would be underrepresenting the flows. We attribute this to higher water usage for irrigation in earlier years, 10 and 20 years ago. The idea being that there have been meaningful water conservation efforts that have occurred lately, and so there is a shift in summertime low flow, stream flow in this system, which is why we wanted to calibrate only to the most recent 5 years. Oh, right, and then so on the left-hand side is the same figure you saw a second ago. On the right-hand side, we now have the peak flow rate. So we have daily averages versus daily peak flow rates. These agree pretty well, and that's also nice to see. The two figures agree with one another, which is to say the triangles plot out in roughly the same shape of a cloud. And then we also see good agreement between the model output and the measured output, the gauge measured data from the gauge on the right-hand panel, with peak flows also being pretty well in line. Everything I've said before was at the STP gauge, the sewage treatment plant gauge, in Lower Aliso Creek. There's another gauge. It's the one at Geronimo Road, and this is our performance there. The model is having a little trouble getting to really low flows that are on the order of like 0.4 CFS or lower sometimes. And we are going to work with SCWRP and make post-processing adjustments to accommodate this. We think we can rely on gauge data and visual observations to identify which model flows are indistinguishable from zero. So this is a limitation of the model, but we believe there's a coherent way forward for the flow ecology analysis.
And not to brush that under the rug, it is a significant issue. This part of the watershed has quite a bit potentially more alluvial processes, so we wouldn't capture water that's flowing subsurface, in this during dry weather. However, the model would want to convey, continue that so that we maintain continuity of, the actual water that's passing through this overall cross section, whereas the gauge is more, it can't pick that up, and the weighting measurements can't pick that up. So it is a bit of a, I think we should be clear that there are going to be certain areas where we say, hey, we got very low flows, but those are indistinguishable from zero. and we can include that override effectively in the ecological assessment that SWRP is doing, and acknowledge that higher in the watersheds, where more water may be bypassing the gauge via subsurface pathways, that this may be needed. So it's not all rosy everywhere, and you have to acknowledge model limitations. But go ahead, Rich.
If we acknowledge those limitations and don't focus on the flows less than 10 CFS, here is the plot of measured peak flow rate at the gauge or measured daily average flow rate at the gauge versus the model output for each of these variables. And there's not serious bias here. We have some more scatter due to a smaller watershed responding to storms or not responding to storms in a little bit more variable way. And I should say the representation of storms in the model is dependent on the rain gauge information, and there's not a rain gauge exactly at Geronimo Road. It's a little ways away in the model. So if a storm cell does or does not pass over this area, that can lead to a point that falls off of the dashed 1-to-1 line here. The take-home message is that the cloud is centered on the 1-to-1 line. We're not over-predicting or under-predicting some of the higher flows at Geronimo Road. That's also reflected here in the flow duration curves. This is another way of showing the reasonable agreement between observed data and model output. What you're seeing on the horizontal axis is flow rates, and on the vertical axis is the number of hours in the 5-year simulation that flow rate occurred. And so we see the highest amount of flow rates occurring in the low flows, not surprisingly, with fewer hours duration for the higher flow rates in this study. The point is that the orange line and the blue line are almost right on top of each other. As we saw previously on the right-hand side in the Geronimo panel, there are more there's slightly more hours at some of the flow rates in the lower range for the model. That's how we see on this graph the model is having slightly higher flows around 1 CFS. So we said about recalibrating the model based on this new constraint that was the information gleaned from the isotope data. We now have actually an improved low flow calibration with a lower bias for flows less than 10 CFS. And we also have a similar or better wet weather calibration, so we didn't lose that while we were making some things better, and that's nice. We also assessed the reasonableness of model estimates at additional locations by using the weighting stream flow measurements. And we do have some residual uncertainty, particularly in very low conditions. You may have heard the phrase, all models are wrong and some models are useful. And we know that this model is not perfectly reproducing the data measured at gauges on every single day of the simulation, but we feel like it's close enough for it to be useful for the upcoming flow ecology analyses and the scenario analyses that we'll be talking about later in this presentation.
So I'll just, I think we've talked about a lot of these uncertainties. We talked about these last time. We've been able to, I think, narrow some of the uncertainties in the model through the isotope data. We still, the stationarity question, we have a point in time now for isotopes. We're extrapolating backward and forward about what that means moving forward. We have, gauging at points that receive both developed and undeveloped land. So, do we really know what our undeveloped and our developed parameters should be, or is there different, also other calibrations that could achieve a similar response? All of these are true, and complement what Rich just said. I think we feel like we have a pretty decent tool here to use moving forward, and also one that that may tell us a lie every now and then, which is something we have to expect from models. So I think we have a few comments coming in on the panel, and I also think that we should do a little bit of a time check. We are, I think, running a little behind to get into the scenarios. Doesn't mean we should cut off questions, but I think it just means that we'll pick up the pace a decent amount moving forward.
Amanda, I don't know why, but I'm not seeing the chat. So if you could continue reading the messages in the chat, that would help.
Yeah, that's great. So Christine mentioned that it looks like the greatest bias at lowest, is at lowest flows still. And then she also mentioned gauge data won't capture the lowest flows, and kind of related is Charles said gauges aren't 100% accurate either.
Yeah,
so I know that you touched on this a little bit. Go ahead.
Then you presented the data on the hourly, the number of hours, and it looked like it was a different result. And so I'm a little confused about that. I put my comments in before we got to that slide. And it looks to me like your duration curves show higher flows at the lowest end than in terms of duration than the actual. So I don't really understand why that's different, but
I think we need to talk about what we're describing as low. I think below 10, if Rich, I guess if we can pull the duration slide back up, we're fitting almost identical below 10, and we also showed that a bias, the total bias below 10 was about 0.3%. So we, on average, I don't think if we define 10 below 10 as the lowest flows, which we've typically done in this, I don't think that we are having a chronic over or under.
Showed that wasn't the case though, so maybe I'm a little confused about what that earlier graph was showing. When I asked the question the first time and you said you were going to get to it later,
yeah,
you had another graph that had the similar orange and blue colors, and it showed the blue line below the orange line. So it looked like you were consistently predicting a lower flow than actual. So I don't know if I'm maybe confused about what that graph was showing.
Blue is always observed and orange is always model output. So if blue is below orange, that means the model is over predicting.
Can you just go back to that graph real quick?
Yeah, this one may be the one that's having a hard time loading and bogging my machine down here, Chris.
Yeah, I think we're interested in the time series figures.
So I think we do need to maybe move forward. I would say, Chris, that you're not wrong that certain parts of the time period, I think we are seeing that we're over predicting flows a little bit, and other parts of and other periods in dry weather we're under predicting a little bit. So we've been playing with we've been playing a game of here we're over a little bit. Oh shoot, now we're back into this. We've now determined the source of the problem, which is that big figure.
Sorry, I think you understand what I'm getting at. So
yeah, I do understand.
We don't need to go back to that.
I do understand what you're getting at. Yep, Chris, thank you. And you're right that there are periods where we're a little over and a little under, and that's an imperfection. I think similar to my response to Amanda, that's to Amber, that's an imperfection that I think we need to decide at some point in the future whether or not it makes sense to try to continue to refine a little further. It's pretty darn close though. I mean, half a CFS or so on 3 or 4.
No, I mean, it looks a lot better, and that's and so I'm happy about that. The lowest low flows are going to be the hardest to capture, and my concern is just that we make sure that we're not taking away the little tiny bit of water that would normally be there and assuming it's zero or something close to zero, when that could be a really important part of the time of year for wildlife to have that water. So I just want to make sure that we've got that right.
Yeah, and so especially when it comes to the very low flows, where the gauge very well, seconding Charles's point that gauges aren't, do have error. It's hard to maintain a rating table in a natural channel, or it's one that has sediment moving around and so on. So that's where we would complement it with the visual screening. The permittees are out at these outfalls once every twice a year, a lot of them. And so we have a lot of visual observations of what flow looks like during dry weather in some of these systems, and have a pretty decent way to kind of override when we, where we say, okay, this is a more normally dry reach versus normally wet. And so that's what we mentioned in terms of coming in with an override that would say, okay, the model is, we're outside of the range of what we can trust the model for in terms of precision. Let's bring in the visual observations, whether water's there or not. And I think that's important, especially given what you just said.
Wonderful. So next, Diana Engel was asking about tweaks to which model inputs were most responsible for the model improvements.
The answer to that is easy. Infiltration parameter, and the infiltration rate in inches per hour of the soil, and the thickness of the lower root zone turns out to have quite a large impact on how much water can infiltrate into the aquifer and thus be available to discharge to the stream.
Thank you, Rich. And then Norman Johns was referring to the Geronimo gauge and the potential sensitivity to measured precipitation not being representative. Could you do a sensitivity analysis with an alternative data source such as PRISM?
Yeah, I can speak to PRISM. That's an average annual data set, that describes the overall average annual rainfall and normals, based on an aggregation of a bunch of gauge data, as well as some really nice algorithms that consider topography and so on. And so it's a really useful data set for figuring out, like, how much average rainfall fell between two gauges that might be separated by a mountain or whatnot. In terms of what we're driving the model with, it's hourly data. So we really need something a lot more, high resolution temporally to drive the model. And the limitation is really just that, any one gauge doesn't ever capture the full spatial variability of rainfall that's happening at a time. And when you have a bigger watershed, you have a better chance that more gauges are contributing. And so therefore, you're more likely to have a time series that lines up with what's been measured. When you have a smaller watershed, it's a lot less. It can be more biased by the model assumption that rainfall fell over the whole watershed all at the same time. So you see some times when there's more flow than what was measured, and sometimes when there was less. On average, when we look at it from a flow duration perspective, it still looks like a nice flow duration curve comparison compared to the gauge data. It's just we don't, and for the ecological analysis, we don't need to know exactly when flow occurred. More that the distribution of flow rates are something that is reliable. And thanks for the clarification, John, or Norman, on the daily data. I wasn't aware of that, but we still need to be driving the model with hourly data. So that was our primary basis for which gauge data we were able to use.
Wonderful, thank you all. Again, the time check, it's 10:53, and we are a few slides away from our break. Thank you.
Thanks a lot, Rich, for telling us about the model.
No problem.
We wanted to also, before we take a break and before we move into reference climate and water conservation results, talk about the hydrologic model that we've received data from Wildemuth and Santa Margarita Water District to describe, that SCWRP is using as the inputs for the regions that I showed earlier. And so we'll take you a quick tour through this model just so you can understand what it is from a completeness standpoint. I'm going to move through it quickly, though, because I do really want to get to the next stuff. Basically, this is a GS flow model, which is a coupled groundwater surface water model consisting of precipitation runoff modeling system and ModFlow. Both of these are USGS software. This was done, previously by Santa Margarita and their consultant Wildemuth to support various basin management decisions and evaluations, but they were able to extract the modeling output at various reaches that could then drive the flow ecology analysis. With two exceptions, we have a few areas where these models overlap. And there's a couple exceptions where we're going to continue to use Lspc. One is Oso Creek because it is a highly urbanized watershed. PRMS and ModFlow operate at a daily time step, which is going to miss some of the peak hydrology and more complicated drainage routing that happens in Oso Creek. In Horno Creek, there was a limitation on being able to extract the model output from GS flow, and so we use that. And that's a similar case where there's a fairly urbanized watershed draining to a structural stormwater BMP that is that we can model in Lspc. And there's in both of these cases, there's relatively little groundwater surface water interaction that occur in the watersheds of these. That really starts where you get down into very lower Oso Creek and into Trabuco Creek and San Juan Creek, where those processes pick up. So that's how we've divided this. And so this is just another depiction of how we've divided up the domain. And so the green you see here are the reaches of primary interest where the flows out of the GS flow model are being used to drive. And I'll note that the GS flow model obviously extends outside of these areas, but these are the areas of interest for this study. So this is the total domain of the GS flow model. And it's the San Juan Creek watershed, nothing different than that. This is a simple depiction of the groundwater surface water, the surface component of this model, the PRMS model. And much like Lspc, it receives rainfall and irrigation. It simulates ET runoff, interflow, and recharge down to the lower component of the model. I mentioned it's a daily time step, and they've run and calibrated this between 2000 and 2016. So it's a little different period, but it's also a long-term period that is useful for analysis. So this is just a simple look at the spatial discretization of the surface runoff. So for large watersheds like Trabuco and San Juan, this discretization is good. In comparison to in comparison to the Lspc model provides a bit more discretization in the Oso Creek watershed. Hence, one of the reasons why we would use that for that more urbanized watershed. So the GS flow model is a ModFlow model. That's a gridded computational surface groundwater flow model. The way these two are integrated, it allows water to flow from the PRMS model down to the groundwater and back up to, if water, if for example groundwater is rising, this importantly accounts for groundwater withdrawals, which are an important part of the hydrology in the Trabuco and San Juan basins, as well as in Gobernadora. So this is just a quick look at the spatial discretization of the ModFlow model, and this is bigger grid cells in the upper parts of the watershed and smaller grid cells to capture the more important processes for Santa Margarita Water District occurring within the main stem of Trabuco and San Juan. So I mentioned that they're using this primarily for groundwater basin management efforts. It's been a lot of effort to calibrate it against the pumping and groundwater levels primarily, but also calibrated against the Trabuco stream flow gauge. And then so we worked with Wildemuth to identify the locations within the model that would be most interesting relative to the flow ecology study. And the what you see here on the red cross sections are areas where we asked for surface flow as well as subsurface flow in the alluvial system that could be used as inputs to the ecological analysis. And so we received those, and then I'll show you later that we also worked with Wildemuth to develop a water conservation scenario involving a reduction in irrigation application rates in the watershed, in urban land, and so they were able to sensitivity test this for how it would look in a future condition where additional water conservation occurred. So that's the real quick snapshot of this model, and it's not the primary topic here, but I wanted to provide a close the loop on some of these areas that are not being served by the LSPC model for the study. And with that, before we take a break, could have time for any questions on that. And I'm not sure if Eric Chang, are you on the call from Wildermuth?
Hi, Eric. I don't think Eric is on the,
okay.
Yeah.
Don, I believe Don Bunce is on the call and could potentially answer questions, although I don't think he's done the modeling himself.
We do have one question in the chat from Christine Medic. How do SMWD models compare with isotope results in terms of contribution of natural groundwater to flow?
I wish I had the answer to that question, Chris. I don't think it's something that is as trackable in those in that model. Although we haven't asked the question of Wildermuth so I'm not sure. I don't have a good answer for that. I think it's worth discussing if there's something that we can extract from their models that would be that would allow a comparison between what we're seeing in the isotope data and what the models are producing.
Those are all the questions on our end.
Notably, this was a model that was calibrated and validated for use in its intended purpose prior to the isotope data, and so the scope of work for Wildermuth and Santa Margarita has not been to reopen the calibration of that model, in light of these, and so we still consider it to be a very reliable model for this watershed, given the complexities and the investment that's already gone into it. But it comes in it's a little bit of a different source to the study than the LSPC model. I promised to be early and I didn't, but we were actually right on time for our break. So shall we take 5 minutes, Amanda? Come back for scenarios?
Yes, we can take 5 minutes. We could take the whole 10 if we'd like. Let's see, it's 11:03. We could come back at 11:10 just to keep on schedule. Sounds good. So we will see you all at 11:10.
See you at 11:10.
Thank you.
All right, Amanda, I'm back whenever you're ready to get going again.
Sounds great. We're ready to go.
All right. Well, so we're gonna move in to the scenario analysis part of the work. Obviously, we care about filling gaps and really understanding the full range of flow regimes in the existing condition, because it helps us, even though we have gauge data at quite a few locations, it helps us fill in the gaps in between those and get an estimate of what's going on throughout time. Scenario analysis is an extension of this that serves different purposes in the study. And so the scenarios we're going to talk through are the reference condition. You've seen this before. And so there's just, I've kind of presented this from past to future. So we have one comparison of what things were prior to urbanization. It's not a specific spot in time, but it is a condition without urban impacts on the landscape. And so same climatic data, same period, but with the differences being the urban influences. We also have a scenario analysis looking at historic global circulation models. So these are basically different climate data on the same exact model of the watershed. So looking at recent history versus future projections. And then in the same direction, taking the same two periods, looking at the current calibration versus a future version of that current calibration where there's a reduction in outdoor water application. So representing a sensitivity analysis on what could become of stream flows in the era of additional water conservation measures within the watershed. So this is an overall orientation to the three scenarios that are we're using in the study. So the reference condition we'll start with, and these are this is a slide you've seen before. Just kind of reiterate, the goal is not to get back to a reference condition. The goal is to look at the impacts that can be attributed to urbanization, and then say how much of those resulted in a change in hydrology. And so a comparison between reference and current gives us that assessment of how much have these factors changed parameters, and so what degree of alteration would things be in compared to a reference condition. But as you've heard us say also, the goal in a lot of these cases is not to get back to a reference condition, but rather to look at how flows may be modified to support the target species, the desired species. So you've also seen this one. I won't go through this again. Basically, it's taken the same hydrologic calibration. We have hydrologic parameters assigned to all sorts of open space areas as well as developed areas. And so it's basically just populating the watershed with the open space characteristics representative of an undeveloped watershed in the area, but with the same parameters we're using in the current condition. Of course, with impervious cover removed, with lawns removed, and repopulated with low vegetation like scrub and forest being dominant ones. Obviously, irrigation is not present in that condition. Any flow control structures and concrete channels get removed, and we really have no idea what stream losses were in a reference condition that doesn't even have a date versus what they are now. And so what we do know is that there would have been a lot more stream miles in a reference condition before it was developed, but that the density of the vegetation would likely have been lower due to less augmented flow. And we see that bear out in aerial review going back to the 30s, that their vegetation was lower, although that's an agricultural impacted condition, so it doesn't actually represent a true reference. So we could dice here all that we want, but what we've done is just assume the same stream losses in existing in reference, representing a greater amount of reach, but a lower density of vegetation in each reach, with losses primarily being evapotranspiration losses. And here's a look at the land use, how it, from current calibrated model on the left. So these are our pervious lands, and then up here are impervious components. And so you see all those go away, the open space low vegetation gets bigger, substantially bigger in the watershed. So what does it mean? What do we see in the results? We see that flows were lower on average in every month. Flows were lower in the reference condition than in the current calibrated condition. Not near as much lower as the previous time you saw this plot. They were off the bottom of the plot last time because removing irrigation the last time had a big effect. Whereas irrigation has a lower importance, not at zero importance, but a lower importance in the current condition model. And so therefore removing that and removing the impervious cover associated with urbanization had less of an impact. So these are our, this is a look at this. And what I guess one of the things that you'll see is that it does suggest that on average, at least we would expect to see some amount of flow in the system in the summertime. And it might be between 1 and 2 CFS on a, sort of a median compared to between 3 and 4 CFS in the current condition. That's a very definitive statement I just made there with a lot of uncertainty, but that's what our model, that's what the model says. So here's a few more numeric ways to look at this. The first line is the average annual discharge volume. First reference, then calibrated, then a percent change. So we see that average annual discharge volume has increased a lot. We know that happens with urbanization. It comes in both higher low flows as well as higher storm flows. The median summer flow, here's a comparison. It's a bit higher, augmented to the tune of a little less than two times, and then a 2-year flow rate, sort of a similar magnitude as being increased to the tune of two and change higher than the reference condition, and similar magnitude for the 10-year flow rate. So we have a sense of how much things have moved. And we can also express this in terms of reference as a fraction of current. So this is saying like the reference was 35% of what we saw, what we see currently. We come back to this fraction again. So to move forward a bit, this is another look at the flows. We see there's not a whole lot to talk about here. In the interest of time, just kind of keep moving on. The comparison to we previously talked about a comparison to Cristianitos, and we cautioned it's not the same watershed. It might not be the same, but here's a way to look at the whether we think we're right or not. Interestingly, Cristianitos is here's a look at the soil groups in Aliso. We have quite a bit of D soils, but a significant amount of B and C soils in certain areas, representing potential recharge zones within the watershed. And then, if we look at Cristianitos through the exact same lens, went from about 64% D soils to about 85% D soils. You see quite a bit less in the way of watershed recharge zones, probably quite a bit more in the way of alluvial stream miles in the system. So they're, just looking at it from a superficial geology and from a watershed shape perspective, from a feet of stream miles, they aren't exactly the same watershed. This one would tend to probably produce less recharge due to higher or due to tighter soils, if you were to think about them on average. So what is our comparison here? Our comparison suggests that they're not measuring flow in Cristianitos Creek during the summer. It's dry. It's being observed to be dry. It's not just a low flow measurement error. It's they're out there. USGS is out there and identifying dry conditions in the watershed a lot of times during the summertime. So the the calibration currently has, tilting us more towards a rainfall-derived recharge, and that the isotope data suggesting that a significant chunk of water in the stream during the summer is originated as rainfall, kind of tells us that that is potentially a more naturally perennial system. and the data we have for Cristianitos suggests that it's not. So we now have a bit of a diverging line of evidence here, and in the sense of our reference condition. So it'd be awesome if they matched, and we had reason to believe they should match. In retrospect, I think there are multiple lines of evidence have led these to diverge, and to come up with some explanations for why they could be different. This plot shows us something similar in the sense that they do, especially when we get up into bigger wet years, we tend to line up a little bit better. The orange line is the Aliso reference, and the blue diamonds are the Cristianitos Creek. So we tend to align a little better up here, but certainly at the low flow range, there's a lot more years where Cristianitos is pretty dry most of the year, and the Aliso reference condition shows us more perennial flow in the system. So average annual plots. So the biggest takeaway here is that our reference condition changed as we tried to align with lines of evidence in the watershed. Through the isotope data, we ended up changing a calibration. We took emphasis off the irrigation component for sustaining summer base flows, and we had to make up for it somewhere, which came from recharge and discharge into the stream during dry weather. And so that led us to depart from the Cristianitos comparison to a greater degree. We do. There is some explanation here that, with Cristianitos having a lot more stream miles to result in losses of water that does seep, as well as tighter soils that would sustain less amount of recharge in the watershed. There is a plausible explanation why these are not the same watershed, geologically speaking, and therefore you wouldn't expect them to match up. So the end result results in a bit less extreme alteration in the existing condition than what we showed previously, not going from a ephemeral system to a perennial system, but rather in Aliso and in a lot of our other watersheds where we saw similar isotopic signature, expecting there to be some perennial conditions existing at least in some years. And I would note that in the dry in the depth of the drought, we did see this go to effectively zero in the Aliso reference condition, in response to the 5 years with very low rainfall. So not always perennial, but more often perennial, at least based on the calibration we have now. So, and I think I've just gone through the supporting lines of evidence. I don't think I need to cover these because I've already done it. I would say that one of the points I'll make right over here on the uncertainties is that there has been a lot of geomorphic change in Aliso Creek. So there's been an extensive amount of alluvial material exported from the creek due to erosion in response to urbanization. And so what a portion of the flow that may have been subsurface in a reference condition through alluvium, may very well now be flowing atop bedrock or some exposed to the surface and measurable now compared to what it was before. So that's a bit of a wild card thrown in there. That's that. And I'll pause for questions I'm going to pause for questions after each of these scenarios so that we can take them one by one. And if there are questions here, we can take them briefly, and also
Wonderful.
Try to keep moving too.
Yes, there is one question from Christine Medic. So due to differing underlying geology, the watersheds are not comparable.
I think there's due to that change, that difference, there is a reason to believe that they may not be have the same hydrologic response. Yes, and then there are other factors that we didn't explore, like faulting and alluvial processes that could also explain differences. So any two watersheds are always going to have potential to be different. There's a plausible explanation why these wouldn't be expected to have the same runoff response, but they are both. So yeah, I guess I'll stop there. And you would, I guess the one thing I would say is you would expect that to be borne out the most at low flows. When you have rainfall in a watershed, over the watershed, you'd expect them to come together a little bit more. So, okay. I think we, unless anybody has a hand up.
Agreed. No, Christine. And then there's no other questions on this end.
Great. So climate. The way we approached this was through it's a sensitivity analysis effectively. We obviously don't know where the climate is going. We have some models that span different projections. We also don't have daily data, we don't have, we do not have hourly data for climate. We only have daily data for climate in the history and as well as in the future. So, while we prefer to run these things with hourly data to match the types of storm intensities that we see generating runoff. In this case, what we had to do is we had to, run the model at daily resolution and use it as a comparison. We did it for both the historic and the present, and the future, and so we can still look at relative differences here. We sample GCMs, which each have a different sort of thought process on how things could change, and we consistently use the RCP 8.5, which is the standard, or the highest of the standard RCPs, representing what has been called business as usual. It's hard to associate that exactly with that, but it is the upper limit. So this is intended to be a sensitivity analysis. If climate changed in a significant way, what would we see in terms of the streams? What I want to caution is that this is not necessarily, this could overstate the what may happen. So the 4 GCMs we picked are the same as what SWRP has used in other studies in Southern California, intended to bracket sort of the projections that tend towards greater rainfall, greater rainfall being the y-axis here, and greater increase in temperature. They all project increase in temperature. So the median of all is at greater than 2.5 C by the end of the century. By 2060. Some of them represent a little less precip, and some of them represent a little bit more precip on average. So these are the 4 we picked to bracket things, and you'll see these presented. You're not going to be tested on remembering the alphabet soup of these. So when we ran these through the model for LISO, we applied, I mentioned the 2 periods we looked at. Everything held equal except for the historic data were run, our GCM run of the historic, and the future is looking at 2030 to 2060. So same period of simulation in terms of 30 years each, trying to hold everything else fixed and just change the climate. So average annual discharge volume. We saw various models predict, some predict higher, some predict lower, within the range of plus or minus about 20% if you had to, sort of bracket it with an average change of near 0 between these 4 models. So we may not see an increase in average annual discharge volume, may or may not. When it comes to median summer stream flow, this is defined as May through October, median stream flow. We see some models predict higher, some models predict lower. The median, the average of these 4, if you looked at it from, again, it's kind of plus or minus 20%, or maybe plus 14 to minus 25% as a range, with an average of these a little less than or a little negative, indicating a minor change in summer stream flow. And you'll see that these absolute values are a little weird because they don't line up with current. When you change from using hourly to daily, you represent a little bit more recharge on your heavy storms, and so therefore it sustains a higher base flow during the summer. So there is a change in absolute values as we go from daily to, or hourly to daily. And so we're really comparing and looking at a percent change as opposed to and absolute magnitude. 2-year peak flow is another place where the peak gets masked, for sure, when you go from hourly to daily, but we can still compare the two together. There's one model that shows that we could see a fairly significant reduction in 2-year peak flow. The other 3 suggest an increase in peak flow. So if we average these 3 out, we end up with a substantial increase in peak flow. Not a ton, but something that seems plausibly higher than what we currently see. And similar with the 10-year peak flow, although models are less certain that the 10-year peak flow would increase. So that's, why don't we take the water conservation scenario next, because these two are both looking from current into the future, and we can take them both together and look at the combined effect of climate change and water conservation, and we can take some comments then. So water conservation scenario, we wanted this to be reasonable. We wanted to sort of bracket an upper range of what people think is reasonable moving into the future in terms of additional reduction in outdoor water usage. And so we consulted with 2 partners in this, Moulton and Santa Margarita Water District. We did a lot of work with Moulton to figure out what level of existing technology adoption exists in the watershed, and then how much further they think this could go in the future. Notably, Moulton has tracked a lot of water conservation, and they've done some surveys to figure out how many people are using different technologies, and so they estimate that moving forward in in additional adoption and additional demand management could result in about 14% reduction in water conservation moving into the future. We asked Santa Margarita and Wildemuth to estimate a realistic upper range for Santa Margarita Water District service area, and their estimate that they used in the model was about 20%. So these are pretty similar values used in these models. Representing the last 20 years of adoption has been substantial, especially the last 10, and that additional adoption of outdoor water conservation measures would somewhat slow compared to the rate of adoption in the last 10 years, but would continue in a significant way. So we then incorporated those reductions into the model. Rich mentioned that we apply irrigation in the model, and that irrigation can lead to seepage. It can lead to runoff from the watershed. We tune that down. So less irrigation will result in less seepage and less runoff from the watershed. I believe Wildemuth applied a very similar approach of turning down the irrigation application rate in the GS flow model, and then ran those simulations and it extracted them out. So first I'll start with ELISO, which was based on the Lspc model. We saw that average annual runoff volume, as we expect, would go down a little bit in the model. One thing that we didn't entirely expect, but we saw, is that the 14% reduction in applied water on an average annual basis turned into a little bit exaggerated in terms of summer stream flow. So we saw a more significant reduction, and this could come a couple ways. Just a reduction in the amount of runoff that occurs in the watershed as a result of overspray, which studies have shown that say a 20% reduction in irrigation or in water usage can also translate to about a 50% reduction in runoff, as that water has a chance, less water, more chance for that water to evaporate in the curb, and so on before it runs off. So it's not exactly a linear one-to-one. The other element of this is just a bit more depleted groundwater, it's root zone at the time when rainfall occurs. So things may not be quite as wet when rainfall occurs, and so maybe a little bit less recharge occurring in the watershed as a result of it being a little drier. So I think we could consider these to be reasonable sort of upper bounds on what we may expect stream flow to respond to reduction in outdoor water usage in the future. So this is coming from a completely different model one run by Wildermuth, and for the and this is extracting flow at the bottom of Trabuco Creek. So they saw a similar reduction in average annual discharge, a little bit more than what we saw, and a very similar median summer discharge. And this is, I apologize for the misspelling here, this is supposed to be 25th percentile summer discharge, and also saw that reduce. So that's the take here. So we bring these all together. We have trajectory from the past to the present, roughly speaking, from a reference condition to a current, from current to the future. And so how does this all balance out? So current to the future, this is potentially the combined effects of water conservation and climate change. So for water conservation, we instead of looking at only the upper limit here, we took a midpoint sort of between half the water conservation and the full water conservation. So you see 8% was what we had estimated. So we took, and half of that would be 4%. So we took 6% as a more realistic sort of projection so that we don't artificially weight this, higher than, on the upper limit of everything. So we see in terms of average annual runoff volume, we see the potential combination of these two could span zero here, but is more likely to be negative. Median summer flow is probably where we get the biggest, the most strong signal. We see, the combined effect of climate and water conservation, which are not really independent, barely spanning zero. There's just, potentially a net zero here, but in a more realistic case, likely resulting in some reduction in stream flow. So with a central tendency of about a 25% reduction. So when it comes to 2-year storm flow, we don't expect the water conservation to influence this significantly, but we do expect there's, the GCMs for climate span zero with potential for a minor increase in 2-year storm flow. Then when we think about going all the way from reference to future, this is where percentages get a little tricky because you increase by 1% and then you decrease by the same percent, you don't get back to the same spot. So instead we use fractions. So if the reference was 35, and we're doing all these fractions as a fraction of current. So if the reference was only 30.35 of current and the future is going back to 0.93 of current, then we're still about 2x higher on average annual runoff volume than a reference. Similarly with storm flow, we talk about an increase potentially in the future, but it's already been increased by so much that it doesn't really change. We still have a model, altered hydrology relative to 2-year flows. And median summer flow is an interesting one because what we end up with is a pretty substantial potential reduction in summer stream flows in the future condition, and moving back towards within about 30% of the reference condition stream flow. So as water conservation occurs, as reduction of urban runoff occurs, it appears to be pushing us back within striking distance, so to speak, of the summer stream flow, the reference condition summer stream flow. So that's just going to summarize the same thing that I just said, which is we potentially the most clear signal coming out of these scenario analyses is that it seems likely that there would be some reduction in summer stream flow, and with the number being about 25%, but with quite a bit of error bounds around that in moving into the future. This would move us closer to reference as we estimate it. And I think this is a shift that is probably significant enough that it would influence the ecological assessment and, you know, help provide some management level guidance as to, you know, which parts of the watershed are shifting in a good way and which parts of the watershed may be shifting in a way that would maybe no longer support an ecosystem that's been adapted to perennial flows. And with runoff volume and peak flow, I mean, these are probably the projected future changes are probably, you know, within the noise compared to how much things have changed with urbanization, such that future changes with climate and with water conservation are pretty de minimis and probably don't require a separate assessment and a separate dimension to the analysis. With that, that's the last. That is the last slide on the scenarios, and so I will open it up for questions on both water conservation and climate change, which I think you'll agree go sort of hand in hand here in how we can interpret them.
Thank you, Aaron. We have 3 chat questions. The first is from Garth Engelhorn. Do the water conservation scenarios account for new development, redevelopment through 2045?
The water conservation scenarios do account for redevelopment. They account for the types of water, additional water conservation requirements that would apply to redevelopment in terms of, you know, taking a location that might have had traditional turf and traditional landscape irrigation in the current condition, and with redevelopment would need to go to based on the various state landscape ordinances and local would need to go to a more water sensitive palette. So that is considered in that. New development in the Aliso Creek watershed is really limited and would need to fully manage its runoff hydrology. You know, both when it comes to just about any of these watersheds we're talking about, would need to fully manage its runoff hydrology relative to both dry weather flows and hydromodification, the full flow duration curve matching. And so we have not considered new development in this, with the assumption that any new development would have pretty much a net zero effect relative to the current undeveloped conditions in the watershed. So I'll take Diana Engel's question. Can you explain how you got to 7% as a midpoint of -19 and 22? It was an average of the 4. It was not a midpoint of the 2 extremes.
Thank you. And then Christine Medic asked, future condition will no longer support current habitat even without proposed reductions, ?
Probably maybe, Chris. I think that's one of the questions that these data are going to help us understand. I think
yeah,
you know,
the question was, are you anticipating right now that we're going to have, even without having any reduction, that we're going to have less water in any case? Is that what you're predicting?
The current versus future GCM span 0% change, with a slight, you know, tendency to estimate less than, you know, or a negative change, like a reduction in stream flow. So, you know, that's this number here you see on the screen. It's small, you know, I mean, obviously the absolute magnitudes of the range are pretty big. And so it could be less, could be more, combined with water conservation, likely yes. And, you know, water conservation comes from like statewide mandates to reduce water, you know, to alleviate water shortages, and this, you know, so these are not independent. You know, this analysis basically says what happens if we change the climate, but we don't change our irrigation patterns at all compared to, you know, what we're doing currently. And this one says, what if we change, if the climate changes, or what if the climate doesn't change, but we do decrease our you know, irrigation to satisfy you know, mandates for reduction. And you know, are these additive? I don't know, but they might be, might or might not be. I think, I don't know. I'm waffling on my response because the climate itself doesn't give us a clear signal, negative or positive. But I think any realistic person here says that, the water conservation, even if we didn't encourage more people to do it, people are still adopting these technologies. It's going to continue, and it's going to, with additional price pressure and with additional water supply, availability pressure, it's going to continue. So the overall effect is likely a significant reduction, although not a 90% reduction. We're talking about maybe a 0 to 50% reduction. I don't know if that answers your question, Chris. I don't have a crystal ball, but I can help interpret the results.
That we're already anticipating a significant reduction even without any additional diversions or water, from, in terms of implementing the MS4 permits.
That's a fair assessment of this, Chris. Yes. It's still above what would be a reference condition, and I think the layer that gets thrown on in this next month would be Eric and Chris and Katie's assessment at SQURP of, sort of what the flow needs are for different targets, target ecosystems. So that's yeah. But your assessment that you just made is correct as far as the models are telling us now. That we would likely expect to see reduction in summer stream flow moving into the future.
Okay, thank you, Aaron. Sandra Jacobs is asking, how are these modeling studies related to the SQURP exfiltration of leaky sewer study, if any?
I would say very, very little, Sandra. But the leaky sewer study probably doesn't have a significant, the leakage from sewers, sanitary sewers, probably doesn't have a significant water balance effect unless they're really leaky, overall in a watershed. That study is focused a lot more on the viral and other, microbiology impacts to receiving waters that could happen if sewers were leaky. So I think the short answer is not very related. Kind of two different questions.
Thank you, Aaron. Norman John, he asks, do the Lspc and GS flow models presented earlier have both hourly and daily versions?
The GS flow model does not have an hourly version, Norman. It's being used to model a larger watershed, one that is more natural and open, and to answer questions related to overall patterns of stream flow, as well as overall patterns of basin recharge and management. And so with that, for those purposes, as well as for the purpose of understanding, stream flow in Trabuco Creek, for example, it's a pretty reliable time step. The Lspc model, we've primarily run and calibrated at hourly resolution. It's being used to model some of the more urban parts of the watershed where the flashier storm systems coming through are a significant part of the hydrology. So it's predominantly an hourly model, although for the purpose of the climate simulations, because we don't have any hourly data moving out into the distant future to analyze, we needed to simplify that model and change its time step down to daily. And we're only using that for sort of a percent comparison of what percent do things change due to climate change. And so in that respect, we're comparing daily sim to daily sim. And yeah, so that's, I think that answers that question.
Yeah, Norman says, understood, thanks. Those are all the questions we have on our side.
So I got 2 slides left. You all have a lot of endurance for sticking around this long. And thanks a bunch for all the comments and questions along the way. Great to have this dialogue. The next steps on this, we've presented a LISO, we've presented, we have a bunch of other areas of the watershed where we're applying these calibrated parameters to the local watersheds using the same hydrologic response units. So, there is some extrapolation here that this, a single family land in Aliso Creek is going to behave similarly to single family land in soils in Salt Creek, reasonable extrapolation and a typical modeling assumption. But those extensions to other parts of the watershed are in progress and in fact, we're just doing the final review of the results right now. We are validating those against the weighting measurements that have occurred in some of these systems over the last few years to confirm that low flows are reasonably represented in these systems as well. That's probably just like what we saw between Christianitos and Aliso, that's the condition under which you might expect more departure between one watershed and the next. And so we are able to validate that using the weighting measurements, and that'll be included in the overall documentation of the modeling effort. And had we tried to include that today, I think we probably wouldn't have met time. So that leads to the next question. Documentation of the modeling efforts, as part of the special study report, and then receiving your comments, including the ones you've sent today and the ones we receive in the future, to prioritize where we want to take this model and the hydrologic work, at least in the as we move forward. So that's, and then you all probably saw the announcement for the SAG tag meeting just coming up in about 3 weeks on December 2nd, where you're going to hear Katie and Eric and Chris talk about what they're doing with these data to assess the probability of flow rate ranges supporting different focal species, and a little bit more about how these data can be turned into then tools that can help folks think about, what flow alterations, what flow management decisions could improve the likelihood of ecological success, and just overall sensitivity of these communities to flow. So that's coming up. And before I take the last questions, I think just to point you to, there's a new webpage for this project that the county has released recently, and you can find the link down there below. And there's if you click on the contact button at the bottom, it'll pull up this contact form, and you can send comments that way, or you can reply to Amanda Abrahamian, and she can forward them along to the rest of the team for us to take a look at.
Yeah. Thank you so much, Aaron. I added an RSVP link into the chat, and then we'll be sending around emails about that next workshop, number 6. We are running up on our noon end time here. We did get 2 additional questions, if we have time to review those, Aaron. So the
Yes.
first is from Sandra Jacobs. What type of projects are you envisioning with these results?
I think we're thinking about that. I think we've learned something through this, and I think Chris Medak's last few comments about, the potential water shortage stress in the systems, it potentially helps us understand, where in the systems you might not want to be pulling any more water out in the form of low flow diversions. But it gives us tools to say, okay, if we have a low flow diversion that's contributing, or we have an outfall that's contributing 1/10 of a CFS, but it's it's one that has some source that we've not been able to identify and is a dirtier one, then we'd be able to understand the relative effect of diverting that outfall on the flow regime in the system. So it's a tool to help understand whether or not a flow diversion would have impacts. I think similarly, if ecosystem restoration work was planned, this could be a great tool to understand both current flow ranges, that and how they could support communities, as well as how they may change in the future, to ensure sustainability of that ecosystem restoration project. I think those are a couple of obvious uses of the data, and I think we can probably have a better and more informed discussion about this in a few weeks, as we talk about focal species and we talk about how what the results of the ecological assessment will look like.
Thank you, Erin. Helen Yu has a couple questions as well. She asks, in the future, can we use different terms to represent sources of flow that might be of different origin? For example, groundwater seeps from rain versus groundwater seeps from irrigation. Sorry if this additional question is, sorry if this was discussed previously in the isotope study. What was used to separate subsurface flows / groundwater seeps from surface flows, especially for imported water that can get into outfalls from both routes?
Yeah, that's a good question, Helen. The groundwater seeps that are occurring in the watersheds that we've identified, that the county and their monitoring team has located and then sampled over time are persistently flowing groundwater seeps, and they have, based on the isotope data, they have both some imported water in them and some rainwater derived recharge in them. So I do think that we can split this along the line of pathways. We can talk about, okay, of the water that's getting to an outfall, what's coming through a groundwater pathway versus what's coming through a direct surface runoff pathway. And then we can also talk about the origin of the molecules. So what fraction of that total water that we're seeing at an outfall or in the stream originated from local rainfall versus what originated from imported water. So that I do agree that it's important to be precise about this, and keep those things straight. I don't think we won't and can't identify like certain seeps in the watershed that are imported water and certain that are rainwater, because in any of the urban areas it's going to be a mix of different proportions. Did that answer your question, Helen? Well enough for now. We can keep talking about that for sure. Yeah, sounds like it. Thank you, Helen.
Thank you so much, Erin and Rich, for all of the great information today. And thank you for everyone who participated. We don't have any more questions coming in on our end, so I think it's a good time to finish off this meeting. It was recorded, and so we will be posting a link to that in our regional clearinghouse, which you can access through our website, as well as where you can submit any further questions you have.
I want to thank you all for your attention throughout, your great questions, and for being really active participants in this study. I think we've seen already through the course of this last year and a half that your contributions, your input, your guidance has made this a lot better, and really appreciate that. And yeah, thanks for hanging in there today.
Wonderful. Thank you all so much.
Thank you.